Welcome back. We're going to continue our study in Unit 3 and work some more in terms of ways that we can use models we can use with youngsters in terms of thinking about addition and subtraction. So let's go fire up this PowerPoint and we will begin our discussion with the notion of closure. Yeah, good times. All right, here we go. PowerPoint. All right, let's go from current slide. All right. So you can see how lovely red words there, closure property. Listen, you remember probably from high school writing things about associative and commutative, and we'll look at those shortly. I decided to start with closure, and closure relates to two ideas. It relates to a set of numbers and an operation. So we're going to basically try to decide if we have an operation in mind, and for this particular set, it's going to be addition. And we grab a set of numbers that we look at. So the question says, is this set closed with respect to addition? So you need a set you're considering and an operation you're going to involve for elements from that set. So, all right, I'll let you read it. It says the set's closed under addition or with respect to addition. Basically, if you can grab two elements from the set, perform your operation, which in this case will be addition, and promise me, guarantee me that every single time the answer that I will get as a result of that addition will be a value, a number, if you will, that I can also find in the set. So closure basically says pick an operation, grab a set of numbers, pull two values out of that set, add them, and then verify, ascertain, if you will, whether that sum is also a member of the set. If it is, for every possible set of circumstances, we say the set's closed under that operation. Okay, so again, you can read this, and it's kind of stuff you've already heard. The thing you got to be careful on closure is, at nowhere does it say that the two elements that you're selecting must be different. They can, in fact, be the exact same number. All right, so you can say, well, I've got this set, I want to pull the 5, and nobody's looking, I'm going to pull the 5 again. You can do that. The two values that are being selected do not have to be distinct. They can be the same guy chosen twice. All right, so I decided I'd create some examples for us, and what we'll look at is a set, and we'll still stick with addition. So we'll try to say, is this set closed? I should point out that if it's not closed, we just say it's not closed. I've had students say it's open. I don't think that's proper notation. So we'll say it's either closed or it's not closed with respect to the operation of addition. Here we go. So there's our set. Looks like it's got a whole bunch of odd numbers, 1, 3, 5, 7, and the old ellipsis dot seems to indicate that we just keep on going. Okay, so we got every possible odd number that you can imagine as long as they're positive. So I'm going to invite you to take two of those values and add them. Well, just for hoots, let's pick the 3 and the 5. And if I add them, I get 8. And I'm sad to tell you that I don't think the answer that I just got, 8, is a member of that set. So holy smoke, I seem to have found an example where adding two of those elements gets me a result that is not a member of that set. So I would have to say that set is not closed with respect to addition. Okay. And obviously the 3 plus 5 is 8. You could grab any two odds, and if you add them, you will in fact get an even. So there are any number of possible odds. All right, now this guy's a little sneaky because the dots are going. And you say, well, I want to add. Well, okay, well, I'll take the 2 and the 4. Well, if I add the 2 and the 4, I get 6. And oh, baby, 6 is not in that set. So we're 2 for 2, it looks like, on no, it's not closed. For the sneaky people, they could do 4 plus 4, and they're still going to get that same output. They're going to say that set's not closed because the answer 8 is also not a member of that set. I think there's one more on here. Looks like we've got 2, 4, 6, 8, 10, and so on. Looks like that's the set of evens. That dot kind of gives us a lot of opportunities. So you would play around here and grab a couple of numbers and add them. And at the end of the day, I think I can probably get you to agree that if you add two even integers, or two even whole numbers, probably better to say, we will get an answer that is also an even whole number. So whole baby, it looks like our third example is closed with respect to addition. So that's closure as it relates to a set and an operation. Properties of addition, you've written this down in a notebook somewhere in pre-algebra. First is commutative, all right? Basically, addition is commutative, and all that means to us is that order doesn't matter. If you do 2 plus 3, you get the same answer as if you do 3 plus 2. So when we add, order is not significant. Who's first and who's second doesn't matter a hill of beans. So a commutative change is a change in order, right? Who was first versus who was second. So addition is commutative. Addition is also associative, and what associative changes are, they're changes in groupings. So if you give a kid 3 numbers to add, and the first kid says, I want to add the first 2 first, okay, and then he's going to add the third one in, and you might have a rebellious Timmy who says, I'm going to add the second 2 first, and then I'm going to add the first one. Yeah, guess what? Doesn't matter which group gets processed first, you're still going to get the same sum. So an associative change is a change in grouping. If you're helping youngsters understand this, your associates are the people that you hang out with. They're the group of friends that you have. So associative change is a change in grouping. Identity element for addition basically says if we add 0 to anything, whether the 0 is the first addend or the second addend, we will in fact get the same number back. So identically, we return the value whatever A was. The identity element for addition is 0. All right, so some properties for us to consider. All right, get a look at it. All right, oh, look, you know what happened there? Who used to be first on the left side is no longer first on the right side. So you've seen a change in location. Who was first is now who was second. So that's, you got it, commutative. All right. Second one, 3 and 6 are grouped on the right side. 6 and 9 are grouped, changing groupings, associative. Cool. All right, the fact that if we add 3 and 0, we get 3, that's your identity element. That makes 0 special. And the last one. Now, this one's a little sneaky, because if you look at it critically, it looks like 3 plus 6 is first on the left side. On the right side, now, you know what? There is not a change in grouping here. The 3 and the 6 are still grouped together on the right side. What has changed is what was first versus what was second. So this is not an associative change. This is a commutative change. A little sneaky. All right, we're going to master some basic addition facts. Frankly, I'm a little sad that kids aren't better at mental math. And I've always said that they'll work on these concepts if we work on them with them. But when they go home, they're playing Minecraft. They're doing other stuff. They're going out and kicking a soccer ball. They're not sitting around thinking about ways to get better at mental math skills. But when we work with them in a classroom setting, we can enhance these skills. And I think that's a challenge for us as teachers. All right. Counting on, we kind of already talked about, you count some things and you continue counting onward as you put the big pile of stuff together. So if you had one pile and had 5 items and another pile had 3 items, you would count up to 5. Then you would continue by saying 6, 7, and 8. And you basically count the items. So it's counting on. You might remember as a little munchkin, getting so proud of 2 plus 2 and 3 plus 3. The idea of doubles is significant. You can extend that and you can go doubles plus 1. So if you do 3 plus 4, you can get kids to see it as 3 plus 3 and then 1 more, because 4 is 1 more than 3. The idea of making 10, I think, is very useful, particularly when you get kids to a place where they have to think about, borrowing and carrying and trading. The notion that 10 is a significant number for us in our number system, I don't think we can overemphasize. All right, in its purest form, you're just saying, all right. This 10 frame thing, I kind of dig. And when I was a little kid, we didn't do this, but you might have. If you have 8 items and they're represented by the little red circles, and you're going to add 4 items to that, and they're represented on that bottom guy by the little blue circles, you can envision taking 2 of the little blue circles and filling in that frame where the red guys live and making 10. And then you still would have 2 more left from the little blue circles. So you would have just done the arithmetic at 8 plus 4, realizing that you made a 10 and then you had 2 left over after you kind of transitioned those 2 blue guys up there to fill your 10 box, and you got an answer of 12. So the idea of having 8 plus 4 being a visual to get to a 10 and then what's left over after you've created the 10, I think is a significant thing for us to work with kids. Again, you can create these little 10 frames that your kids can use as they add. The idea of doing things with your hands is what we play with youngsters as we talk about addition and subtraction. All right. The idea of counting back, adding 9 is hard for kids. Again, you get the mental flashback of having to carry and borrow and all of that stuff. And sadly, for a lot of kids, mental math is a challenge. But the idea of adding 10 is pretty easy. And what we get our kids to realize is if we're asked to add 9, we could add 10 and then take away 1, right? Because the difference between 9 and 10 is exactly 1. And your author is very good, I think, in saying, look, in many problem cases, you could use a variety of these strategies. But again, I echo what I said earlier. If we stand in front of the room and we talk about ways to get an answer quickly mentally and provide opportunities for practice and have kids say, this is what I did, I think we can get kids to enhance their abilities to do math mentally. I'm not a Luddite. I know calculators are not going to go away, but I also think it's probably our challenge as the presenter of the content to help our kids to be more adept at doing things mentally. And I don't think one necessarily precludes the other. All right, we're going to look at some addition algorithms as we continue our work on Unit 3. Okay, some of you might remember base 10 blocks. I've got some here in video slides. It's a little hard to see here. If you've got base 10 blocks that you can demonstrate this stuff, that's the way to go. Obviously, the PowerPoint's a little difficult in that sense, but I tried, and you'll see what we got going on here. I'm not going to go ahead and click this, but what it is, it's a means where the instructor shows how, by using base 10 blocks, that you can perform addition. So I'll let that for your leisure, and you can check it out. All right, here you go. We're going to add 14 and 23 by using base 10 blocks. All right, for those of you who don't remember, base 10 blocks have different shapes. You get those little single guys, I'm going to call them nubs or whatever, singles if you wish. So in the first circle, you've got 14. All right, the 10 on the 14 is represented by that stick. All right, so that's worth 10 of the little guys, and 14 would be 1 stick and 4 littles. The second circle has, you guessed it, 23. That's 2 sticks and 3 littles. And if you put them all together into the third circle, holy cow, it looks like you have 3 sticks and you have a total of 7 littles. So the correct addition arithmetic is 37. Again, the advantage for kids, they can see it, they can move it, they can touch it, they can hold it. It's not some concept that is totally foreign. The idea of carrying and borrowing that we're going to come up shortly is problematic for kids. Here, it's real. They can actually say, oh, cool, I put them all together and I see that I have 3 sticks and I have 7 little nubs. All right, so if we're going to add now bigger numbers, all right, so you got 186, and across the top, you've got 1 flat, you've got 8 sticks, and you've got 6 little nubs, and across the bottom, you've got 1 flat, that's 100, and you've got 2 sticks, and you've got 7 little nubs. And your challenge is to say, well, I'm going to add those things together. So you start with the little nubs, and you see we got 6 and 7, that's 13. So holy cow, I can trade 10 of those and get me another stick. And that's the notion of carrying that you and I are familiar with from math. And here you actually get to see it. You get to touch it and hold it. So that's why this is an advantage for youngsters when they're first starting to do the arithmetic. So we will trade 10 of our little nubbies and we'll get 1 more stick. All right, and that leaves us 3 little nubbies left over. Now we'll count our sticks. All right, and you can see, well, holy cow, now we got, it probably looks like we got more than 10, and as a matter of fact, we do. So what we'll do next is we'll trade 10 of those sticks, and we'll get another flat. So 10 tens is 100, so we'll trade in our 10 sticks to get a third flat. That leaves us with just 1 stick, if you will, and now we'll count the flats, and it looks like we have 3. So you can kind of see that the arithmetic that you and I are used to doing over there with our algorithm is what's done. The advantage with base 10 blocks is the kids get to see it and touch it and hold it. And the idea of carrying is much more significantly enhanced when you do the manipulatives. All right, addition algorithms, partial sums. Some kids are bothered by the fact that when you do math, you don't go left to right. So I kind of like this one in that you can go left to right. So I'm going to click and we're going to do the next problem. So what we're going to do is we're going to add from the left. So we're going to do 6 and 7. You guessed it, that's 13. The thing you got to caution the kids here is where the 13 sits. That's hundreds. So make sure that they write that as 13 hundreds. And I think the 2 zeros are significant. The next adds the 5 and the 3, and that's 8, but it's in the 10 spot. So remind the kids that that's really 80. And then our last add is the 6 and the 2 for an 8. And now we'll just add those guys and we'll get, you guessed it, 1,388. So should you have a kid who says, I don't like math because I have to work from right to left, here's an option where you can allow the kid to go from the left to the right. And I'm not so sure that it's not better in this context, working from the left to the right. All right, so left to right addition. Another example, sure, why not? We had the 3 and the 4, that's 7 in the 100 spot, 700. 4 and 2 is 6 in the 10 spot, 60. Careful on the 7 and 6, that's 13. Make sure the 1 floods over into the 10 spot. You guessed it, total 773. That, my friends, wraps down video 2. We'll be back shortly with video 3 for Unit 3. See you then.